event. Just wanted to mention that next week, after lunch at 2 p.m., there will be an interesting celebration on the interface between art and science, and that will start in the library and then end up in my office, where there is, yesterday there was a bronze sculpture delivered of Galileo Galilei, which we all celebrate as a great astronomer, but also a scientist that established the foundation of modern science. So the bronze sculpture arrived. The sculptor, who is very highly regarded, his name is Greg Wyatt, and he produced a lot of sculptures, including at universities like Columbia University and also Harvard, and also New York City, Washington, D.C., many places. He will be here as well, so you have an opportunity to learn how to make a bronze sculpture, which is not easy, by the way. It's also very heavy. So that's next week at 2 p.m. Everyone is invited. The second thing I wanted to mention is we have today the pleasure of hosting Joe Silk. I'm not sure if he's
over there.
Oh, over there. And just for the young people here who may not know, Joe actually graduated from our astronomy department in the 60s. Now, my question to the young people is, do you know what his PhD was about? Does anyone know? Anyone above the age of, let's say, 30? Does anyone know what was the PhD thesis about? No? Okay, this is a lesson in history. He was advised by David Laser, but who was working on cosmology at the time, and Joe had the insight that around the time when the microwave background was discovered, that in fact when you go to small scales, photon diffusion damps the fluctuations. We see that in the most recently the Planck data, but you know that was Joe Silk's insight. It's called Silk damping. Fluctuations are damped in the baryon photon fluid when the microwave background decoupled at a redshift of 1100. Why is that important? Because we wouldn't exist given this effect if there was no dark matter. Ordinary matter, baryons, were coupled to the radiation, and all fluctuations on the scales of galaxies were damped by the effect that Joe discovered in his PhD. So that means if there were only baryons, galaxies would not exist, because everything was smoothed out on the scale of galaxies. However, the dark matter was not coupled to the microwave background, and that's why galaxies exist, because the dark matter kept memory of the adiabatic fluctuations on galaxy scales. So dark matter is really the reason that we exist. We just need to find out what it is, right? We've been trying for 50 years. It's really disappointing.
It is. It's embarrassing.
Yeah. We get paid even though we don't know what we're thinking about. Okay, so Joe will be the first speaker today. He spends his time between Johns Hopkins and Paris, France. And he will talk about indirect detection of dark matter. What a perfect match. And then Yoki Hernandez from Pittsburgh is over there, who will tell us about designing the next generation baryonic acoustic oscillation experiment based on emission line galaxy target selection for DESI-II. Then we'll hear from our own Olga Borodina. Where is Olga? Yes, she plays soccer, and we always have a tough match when she plays. The faculty has a hard time, and we look forward to hearing about the science that she did on the propagation of low, moderate power AGN jets through turbulent interstellar media. And finally, Peter Williams, also from the CFA. Where is Peter? Up there. Will tell us about DASCH data release 7, a century of photographic data from the Harvard plate skies. We'll start with Joe.
the microphone?
We need the microphone.
We need it. It's on, right. Okay, so it's a great pleasure to be here. You know, it brings back so many memories, actually, in this very auditorium when we used to have our square table seminars that were inaugurated, if you can imagine this, by Harlow Shapley that long ago. Those are the glory days of the Harvard Observatory. Anyway, and of course it's back to another stage of glory, I hope now. So anyway, what I want to tell you about is something intriguing in the dark matter field that I've been working on with colleagues in Potsdam mostly. And so let me just give you the basic story before we show you one or two examples. There is precious little evidence for indirect signatures of dark matter. In fact, I would say there's only one piece of evidence for indirect detection of dark matter. Of course, direct detection doesn't work at all. We have nothing. So indirect is our best bet. And this one piece of evidence is highly disputed. And I'm going to describe to you that dispute and how it's maybe beginning to be resolved. Okay, so the story is that dark matter is most plausibly a weakly interacting particle, from the reasons you just heard from Avi. And there's a beautiful argument that comes from freeze out as the universe expands of interacting particles, weakly interacting particles, which tells you precisely what the relic abundance of any stable dark matter particle is. And it particular gives you prediction of its cross-section if it were to interact too weakly with matter or with itself, actually, because it's a self-annihilating particle. Too weakly, there'd be too many of them. If it interacted too strongly, there'd be too few. So you know exactly what the properties are in the simplest models of this dark matter candidate. And for many years, it was thought to be a supersymmetric relic as the most plausible explanation. That's still true, even though we haven't found supersymmetry yet, but there are experiments underway to search for this and hopefully find candidates for dark matter. Anyway, we have this WIMP, as it's called, weak interacting massive particle, which annihilates with itself. It's typically in the 10 to 100 of GeV mass range. And when it self-annihilates, the annihilation products include gamma rays in the GeV range and neutrinos and other things. The gamma rays are the most visible of these products because they interact with the hadrons in the galaxy. And they can also be detected by a telescope, in particular the Fermi telescope. And the most amazing part of the story is that before Fermi was launched, in work led by Doug here, among others, there was a prediction from the so-called Fermi, what were later called the Fermi bubbles, but featured at the center of the galaxy, that dark matter annihilation was a plausible explanation of features one was seeing in different wavelength bands. And if so, there should be a gamma ray signal as a consequence. We saw the other indirect signals in the morphology of the center. And then Fermi was launched, and lo and behold, one of its early discoveries was an excess in the central few degrees of the galaxy of gamma rays. And this made many of us very happy in the particle community, but of course, it's a controversial result. And you have to really test it in every possible way. Had we actually discovered a significant signal? Well, the good news is that over nearly 15 years of data, the significance of this excess has been tested in many ways, and it's now a 40 sigma effect. Okay, so it's incredibly significant compared to the standard other uncertainties in the Fermi data. I mean, people have studied cosmic diffusion and God knows what else, everything possible. So we have a very significant excess of gamma rays. So in the meantime, of course, one should really test any theory like this with every astrophysical hammer available. And the main one that's come up over the years has been the millisecond pulsars, also discovered as gamma ray sources by the Fermi telescope. Now, if one has an excess of gamma ray pulsars in the center of the galaxy, and these are recycled, rapidly spinning neutron stars in binaries typically, that give you the millisecond, many of the millisecond pulsars because they're in old stellar populations. So if you have these, and you're willing to wave your hands a little bit, not very much, you can deduce that this is an equally plausible explanation for the diffuse excess in the central few degrees. So as of up till very recently, up till now effectively, we've had two competing theories, one from the particle physics, dark matter sector, and one from the astrophysical sector, which most people consider are probably equally plausible, but obviously there are strong advocates of one or the other. And let me tell you what are the major criteria. There are three criteria that we look at to try to tell us which of these is the better theory. You have to pass three tests. Okay, so one test is simply the normalization, the strength of the gamma ray signal. So dark matter passes that with flying colors because its cross-section is basically inferred from very simple freeze-out physics. You know what the density is from simple arguments about formation of the galaxy and the central, dark matter profile, etc. You take the standard NFW, whatever that is, profile, and lo and behold, you get the right flux for the dark matter. So the flux seems to work. The second test, that same test, I should say, has equally applies to the millisecond pulsars. But let me come to that in a second. Let's go on to the second test first. The second test is the spectrum. So dark matter has this very beautiful prediction. It's a certain mass particle, the lightest of these supersymmetric relics in the simple theory, which might be 50 GeV or something, that is the candidate for the dark matter. All the others have long since gone. And this particle, clearly when it annihilates with itself, is not going to give you more than 30 GeV photons, right? You're never going to exceed the rest mass, and normally you make 2 photons per annihilation. So that's roughly 50 GeV. So you have a very clean prediction. The spectrum should be exponential or even super exponential. Well, we haven't measured it in that much detail yet. This will come. And so that's the second test. And the third test is the morphology. And this is the most critical issue of all, in my opinion, as you'll hear in a moment, because the morphology for the dark matter prediction has up till now, in probably hundreds of papers, been very simplified. It consists of a spherical ball of dark matter with an NFW dark matter profile. On the grounds, that's what dark matter should be. Now, on the other hand, let's turn to the millisecond pulsar. So they basically are signatures of an old stellar population. And so that old population you can measure now by looking at the bulge. And one of the models, the so-called Coleman bulge, is the one that's preferred by the advocates of the theory. There are other models not too dissimilar. And use that as a tracer of the morphology of the gamma rays. And lo and behold, the gamma rays are not spherically symmetric. They're a bit squashed, triaxial. And the bulge component of the old stars, proxy for millisecond pulsars, fits that reasonably well. Okay, so that seems, that's passed that test with flying colors. The other tests, the millisecond pulsar hypothesis passes too. First of all, you have this question of the normalization. Well, you need enough millisecond pulsars. So it turns out if you take the ones we see with Fermi, the excess near the center, that's not enough. You have to postulate a population of more diffuse, less luminous ones, giving you more diffuse emission. And that you can do. There's no rule against that. So again, they passed the test of normalization when you add some unseen till now pulsars, and then people debate whether they see fluctuations or not, whose gamma rays. That's a debate that's not been resolved to date. It's been very controversial in the past. And so that's that. And then the spectrum. Well, this is really interesting because the millisecond pulsars also seem to have a spectrum very like what we observe for the Fermi excess. There is definitely a power law tail in many millisecond pulsars, and it's something that we can't actually measure yet very well, but this is a job for the next generation of gamma ray telescope, most specifically the CTA, the General Telescope Array. Anyway, So what have we done that's an addition to this field? So with my colleagues in Potsdam, we've looked at what are called constrained simulations of the Milky Way. Now, it's no good, going to some computational group and taking, any model of the Milky Way and trying to zero on the center, because you've got to get the history right. That can affect what we see. In particular, the Milky Way had a major merger, as we've learnt from the Gaia data, and was suspected even before that data, after 3 billion years, and many smaller mergers ever since. So just thinking of that, it seems incredibly unlikely that it will be spherically symmetric in the dark matter distribution. But it's very hard to test that because we need resolution, sub-kiloparsec resolution, to look at the center of the dark matter. And up to now, that's been lacking. Okay, so move to Potsdam and the Hestia collaboration. They are able to bring to bear exquisite resolution using the past history of the Milky Way, the merger history, as more or less inferred from Gaia, etc. So they have major mergers. And lo and behold, when you then look at the dark matter within the central kiloparsec, and of course, what you then have to do is to take not the dark matter in projection, but integrate it, because it's a quadratic effect, a self-annihilation. You take the square of the dark matter density, and lo and behold, you do get a non-spherically symmetric profile, which is hard to distinguish from either the millisecond pulsar hypothesis or the data itself. So let me just show you briefly what this all looks like. So on the right here, you have the data. This is from the Fermi, some dozen years or so of Fermi data. You can see the excess, they've subtracted all the obvious culprits, and you can see this excess peaking out over degrees. And this is a recent model of the Coleman bulge as proxy for the millisecond pulsar, and that you see is, certainly fits better than something very symmetric. And then here we are now with the results of the simulations of dark matter. And so this is the dark matter projection for 6 different examples of this proxy Milky Way from the constrained simulations, and they all look, reasonably similar to the data. And here you take the square of that profile, and that's, is indistinguishable, I would say, from the old star population predicted by the same simulations as well as the data for that matter. So that's the story, basically, and that's why I gave him my title. I think the odds are increasing now. It's by no means much stronger than 50-50, I would say, but it's a question now of we can't say that one model outperforms the other. Both passed all the 3 tests, dark matter annihilation, self-annihilations, or millisecond pulsars. Let's wait perhaps for the CTA to start producing data in the next couple of years, and we'll see if there indeed is a power law tail in the gamma rays. That will be very, very hard to explain, but not impossible by the dark matter advocates. They're very ingenious, but there certainly is a prediction of the pulsar theories, and perhaps a better test of granularity, etc. That will come too with better data and better foreground subtractions. That's the end of my story. Thank you.
So Joe, the center of the Milky Way is about 8 kiloparsecs away, but there is another center of the Large Magellanic Cloud 50 kiloparsecs away. Why do we see any gamma ray excess there?
I think that's debated. I believe recently there has been claims of a slight excess, but I think it's not a very strong signal, and the same is true for M31. There's also an excess reported there, and again, I don't think we have nearly the precision that we do when you develop competing cosmic ray diffusion models or whatever to have the same precision we have for our galactic center.
Would you predict to see it in these models?
Yeah, so the main prediction of these models, I should have said, are dwarf galaxies, which are much cleaner than the LMC. So they're dark matter laboratories. So the idea is you look at the nearest dwarfs, yes, okay, and look for an excess gamma ray signal. And that would be a direct test, because you don't expect that many. With so few stars in them, you surely shouldn't get an old star millisecond pulsar signal. So that's been done It turns out that the Fermi collaboration is now stacked, 20 or 30 nearby dwarfs. They do not see a definitive gamma ray signal. There is one claim that you do see a signal. You take one of the nearest of these low surface brightness dwarfs, some 10 kiloparsecs away, and that has been looked at exquisite detail. Unfortunately, there is 11 stars that they could get spectra for in this system, and when they take those 11, they seem to have a detection. When they take out one of the stars, it goes away because of huge uncertainty. So the answer is we have not passed the dwarf galaxy hypothesis, but that's a firm prediction of the dark matter model, that's for sure, and that will come again in the future.
We had a talk yesterday at a high energy seminar about axion dark matter as an alternative explanation. And they have this kind of falsifiable prediction of small-scale fluctuations that you might observe using different techniques. What would be the falsifiable prediction, except the gamma ray access from dwarf galaxies that you can, that is really hard to get to that?
So the simplest one I would say would be is there a non-Gaussian tail? Because if it's a dark matter annihilation, you expect a very clean prediction. So if CTA sees something, extending to higher energies, that to me would be a hammer blow against the dark matter model.
But axions cannot annihilate.
Sorry?
Axions do not have an antiparticle.
Yeah, I mean,
It needs to be something else.
The paper was the talk was about a paper published in Nature Astronomy.
So, but was it annihilation? Or
No, it was not
Yeah,
annihilation. It
that's
was
the
just the direct
Decay.
the observation. No. It was not the decay. It was the observational effects that the density fluctuations in dark matter could be observed, like using if you look at multiply lensed quasars, because you would expect small scale density fluctuations.
Yeah, I think the axions
Related.
interact electromagnetically and you get some sort of high energy signal. That
Yeah, like lensing
that's
stuff.
right, yeah.
Lensing stuff.
Okay. Please.
This is great. Thanks for sharing this with us. And I think the approach to use SK or different and similar constraint models of the Milky Way is a very good path forward. But I'm wondering whether you have thought about the alternative. We have now fantastic and very high precision mass models of the inner kiloparsec of the Milky Way, with different bar components, the nuclear stellar disk, and all that stuff. That could be an interesting alternative to test these predictions, right? Both on the dark matter part, because they constrain now the dark matter that you can squeeze in order to be still consistent with the observation data, or on the old stellar population, because that is what they directly would predict.
Sure, that should be something, a great test for the future observations with CTA especially, because with enough signal to noise, you can look for signatures of bars or whatever, perhaps in the diffusive issue. That I don't think we can do that yet, far from it, but in the future that could be an interesting test.
Yeah, we have been discussions in Heidelberg to make predictions based on these mass models.
Yeah.
But one thing to keep in mind, in the center of the galaxy, dark matter is subdominant relative to the barren. So,
Exactly.
so you don't get a tight constraint on such a density.
Exactly. This is why you need to make explicit predictions for the other mass models to see the residual and constrain the residual, because up to now it's unconstrained by a factor of 10 to 100.
Yeah, I mean, to say it's subdominant just is not enough. You really have to have a much better feeling, measure of the stellar mass distribution, the streams, whatever, velocity dependence too, etc. All of that comes in. In fact, that's true for the dark matter too. We know that if the dark matter itself, which could be self-annihilating, has some non-Gaussian velocity distribution, that will also, in some models, affect the spectrum and so forth. All those are physics effects we have to, use to improve our models. So this is work to be done to confront the next generation of observations.
Well, let's thank Joe.
Testing. All right. Can everybody hear me? All right. Hello, everyone. It's a pleasure to be here. My name is Yoki Hernandez, but everybody just calls me Yoki. And I'm a fourth-year PhD student at the University of Pittsburgh, working with Jeff Newman and Brett Andrews. And today I'm going to be talking to you about target selection of emission line galaxies for DESI-II. And in particular, by the end of this talk, I hope to convince you that we'll be able to obtain highly redshifted ELGs, or emission line galaxies, using LSST imaging, and that this is, in fact, how we should approach dealing with current systematics with the current ELG sample in DESI. So let's begin. So a bit of background. Let's talk about what baryon acoustic oscillations are, or BAO for short. So BAO is an imprint from the early universe, back when matter and radiation were coupled, that manifests today in the clustering of galaxies. So in this animation of the mass profile of a single overdensity region as a function of the radius from the initial location of the overdense region, this is a credit to Daniel Eisenstein, who I see in the back. But what you'll see here is a simplification of what was actually happening, but it tells the story nevertheless sufficiently. Dark matter is in black, baryonic matter is in blue, photons in red, and in green we have neutrinos. No one cares about neutrinos. Just kidding, we do, but not for this talk. So what happens is an interplay of two forces, mainly gravity and radiation pressure. So gravity wanted to pull things together, but because there were so many photons compared to baryons, this created immense spherical waves that propagated outward. And because we know how long these waves could travel before the first neutral atoms could form at the epoch of recombination, we now have a feature of known size in the early universe that we can use as a standard ruler to trace the expansion history of the universe. So to measure this signal, you require a large, dense sample of galaxy redshifts, and it's sensitive in particular to incorrect redshift measurements. So not too long ago, DESI released their year one BAO results and got something interesting. So in this Hubble diagram, we have the distance we'd measure using the BAO, scaled out by the fiducial lambda CDM as a function of redshift on the x-axis, using all of the DESI tracers, and the dotted, dashed, black line corresponds to the best fit to the DESI data. And what you see is there is a deviation from the fiducial lambda CDM paradigm. So this is interesting. Right now, it's near the 3 sigma level, but DESI has more data to collect, and hopefully as we collect more data as we near the 5-year survey, we can figure out what has actually happened, if this is an actual measurement of a deviation from a cosmological constant, which is the current model for what dark energy could be, or if dark energy is in fact evolving with time. So let's talk about what emission line galaxies are, or ELGs for short. So ELGs, unsurprisingly, are galaxies with strong emission lines. In particular, for DESI, we're interested in the O2 doublet feature, which spans a very narrow wavelength range and allows us to get a reliable redshift measurement relatively quickly if you can measure that in the spectrum. And the ELGs for DESI are going to be most powerful at redshift 1.1 to 1.6 to provide the best large-scale structure constraints, specifically because they span a larger volume. The ELGs will make up a plurality of the sample that DESI is collecting of large-scale structure tracers, making up around 33%. In this histogram here, we have the number of reliable redshifts per square degree as a function of the spectroscopic redshift. And these are the current ELGs that DESI has collected. And what you see is we have a low number density tail as you go up to redshift 1.6, where it cuts off, marked by the dashed vertical lines. And this is not the best, because we want to make the best use of the instrument, and having higher redshift ELGs, a larger, denser sample, would be very great for reducing errors in BAO measurement. So we want to increase the sample size, but by how much? Well, Here we have the BAO parameters for both the perpendicular and line of sight, which gives us information about the angular diameter distance to some redshift and the Hubble constant at some redshift. As a function of the number density, the average number density of the ELG sample, normalized to DESI. So DESI is currently at where the solid vertical line is, at 1, and the dash line here marks our target. The reason we're targeting around a factor of 4 increase is if you look at the different redshift bins colored in red, orange, green, and blue, specifically at the highest redshift end, we see that we get a decent drop-off in errors around a factor of 4, but increasing past this point really won't help reduce errors much, and you get the point where you're just hitting diminishing returns. So let's compare the ELG sample to another DESI tracer, the luminous red galaxies, or LRGs. So in this panel here, on the left, we have the LRG correlation function in red, measuring the BAO peak. Beautiful. Compare that to the ELG measurement, and it's not so beautiful. We have larger errors, and you might be wondering, well, why? Well, let's compare now the sky map of the target density for these two samples. The ELGs in the top, or the LRGs in the top, and the ELGs in the bottom. Looking at the sky map for the LRGs, it's very uniform, which is great. You want to make a very uniform selection as to not introduce selection effects that could be misinterpreted as a cosmological signal. In contrast, we see clear depth variations across the sky for the ELGs, and the reason this is, the consensus within the collaboration, is that the ELGs were selected too faint, so near the limits of the photometry used for targeting, and that made it susceptible to systematics that affect depth. So the idea is, if we use better imaging to target our ELGs, we should be able to get a more efficient and denser sample than what we currently have. To demonstrate this, here's a patch of the sky from the Legacy Sky Survey, from the Legacy Survey viewer, using the GRZ photometric bands that DESI used for their targeting for ELGs, and the corresponding 5 sigma depths for HSC and LSST. Same patch of the sky. Now we're viewing it with the HSC imaging. See how much clearer that is? And you can imagine this can circumvent the issue of having to target faint if we have deeper imaging, and can circumvent the issue of having to target fainter by just having deeper imaging. The HSC imaging also has additional passbands, I and Y, which are useful for breaking redshift degeneracies. HSC here is a bit deeper by about half a mag compared to the LSST, or what we will have with LSST in year 2, but nevertheless, it's a good prototype. So to do this, to design a better target selection, we used the spectroscopic truth sample. Now, the systematics in the ELGs were so bad that we had to actually test how these systematics were affecting the final sample. Here in this color plot, we have the galaxies that were obtained of this sample. The cuts used to obtain it are in solid black, and the selection box for the current DESI ELGs are in the solid gray. And the idea basically was to get everything that could scatter into that gray selection box and test how that affected your final sample. I should have mentioned this before, but these galaxies are colored by their spectroscopic redshifts here. And for this, we used the wide HSC imaging to make a fair comparison to what we would expect with the imaging from LSST. So after using this sample and optimizing, using the additional I and Y band, we were able to obtain a sample that has very low contamination of low redshift objects and optimizes for redshifts between 1.1 to 1.6 here in blue. Again, galaxies are colored by their spectroscopic redshift, and the arrows point where the sample lies. And to make a fair comparison with DESI also, we used a similar exposure time and a G-fiber limiting magnitude to what DESI used for their ELG selection. So let's really compare. So again, here we have the current ELGs in gray. Now we add our sample here in blue. And you can see the difference. We have a lot more targets within the redshift range we're interested in, marked by those dashed vertical lines. and we reduce the amount of objects outside of the redshift range. I'll finish up quickly. Now let's compare some numbers. We do better at getting reliable redshift measurements, Z success rate, getting reliable redshift measurements in the correct redshift range, 1.6 to 1.1 to 1.6, and we obtain a more efficient and denser sample using a smaller target density. So this is great. We've shown that this is possible, and with what LSST will provide, this is clearly something that can be done and should be done. It should be a high priority for DESI. So I'll conclude now. So we used LSST-like imaging from HSC, which has GRI, Z, and Y bands, to select a clean and dense sample of emission line galaxies and show that we can do this for DESI-II with LSST imaging. If we were to combine the current ELG sample with our sample, we would be able to help reduce errors in the BAO measurement by around a factor of 2 compared to what DESI can do. And this can potentially be done during gray time. Gray time is when the moon is up, but not completely full. And the reason this should be is because moonlight scatters mostly in the blue and affects the continuum. But for our case, we're interested in narrow emission features in redshifted, highly redshifted ELGs. So this means that there's less pressure to take away from the other tracers that DESI-II will use for future BAO measurements. Thank you.
So, Yoki, if you had to make a prophecy as to what the future data might show, would you guess that the cosmological constant is a constant or not? What would be your
That's a tough question. I'm glad you said it's a guess, because it definitely will be. But for the sake of
It's recorded by the way.
for the sake of job security, I'll say more data needs to be taken.
Good answer. Any comments, questions? Yes, please.
I was a bit puzzled. Your starting point for realizing there was a problem was higher densities in the ELG distribution on the sky localized. And I don't see how that's tied to the having too low a threshold in your magnitude.
Sorry, can you repeat that question? Just to
Well,
make sure.
I think you told us that the problem was that they weren't going deep enough and so they had photometric errors. But I don't see how that leads to the spatial non-uniformity.
That's a great question. So in this color plot, right, if there are systematics that affect the true measurement in flux measurements, then if we don't actually measure the true intrinsic brightness of an object, the objects that we do want could scatter out of the selection box here. And vice versa. The objects we do want at the redshift we care about could scatter out. And that is what I meant by the photometric errors, the systematics that are systematically making things scatter out of the color space that we're interested in for the galaxies we want.
So is it just that those high density regions were deeper imaging?
Let me go back to the sky map.
Yeah, the little red areas.
Yeah, those patches of denser and less dense regions are the points that were affected most by the variation in the imaging, since you were closer to the limit of the 5 sigma detection. That is where things begin to scatter in and out, and the uniformity of the sample decreases.
Okay. Well, let's thank Yoki again.
Work? Okay, great. So, hello everyone. Last time I presented at the ITC lunch, I asked you to imagine what if colleague texts you and asks a question about science question. And this time I will suggest you to keep practicing our imagination, and let's imagine that this time a colleague texts you and asks you about AGN jet propagation. And the reasonable reply you may have is, well, why should we care about it? And I want to start with this beautiful image of Cygnus A radio-loud AGN jet. And you can see that this is a very powerful jet. We see this beautiful lobes going out very far away from the host galaxy that is depicted in the very center by this little dot. And even though it's very beautiful and it's very exciting to study, most of the AGNs don't look like this. In the reality, most of the AGNs are really tiny sources, and if we get to resolve them, because they are really tiny, they can be less than 3 kiloparsec extending far from the black hole. Even if we resolve them, they look really not that exciting, maybe. But to me, it's really cool because we see this asymmetric structure, we see these bubbles, and most interestingly about the sources is that they're observed in different types of galaxies, like elliptical galaxies, but also disk galaxies. And based on the radio spectrum, they're not always young progenitors of FR1 and FR2 galaxies, because they're continuously driven by the black hole. And in order to understand how these jets can be formed and how they can be so tiny for so long, we decided to simulate these galaxies, these jets. And we start with the ARIPA code. Effectively, I set up my simulation box as 1 kiloparsec box because of the periodic boundaries. And I continuously drive the turbulence so that initial uniform box creates this multi-phase gas. And while I inject energy via turbulence, I also take it away via cooling. Currently, this work is purely hydrodynamic, so we don't have many other physical effects, but that's ongoing work. I'm still in my PhD. So this is how this simulation looks like. You can see here the box with the mean number density 20 particles per centimeter cube and Mach number 4. And the light regions here show the dense part of the gas, and dilute gas is depicted by the dark regions. And so now we have a turbulent box. Now we will put there a jet. So we are using the prescription developed by Rainer Weidenberger, who was a postdoc here a couple of years ago, and we put jet injection region in the center and launch jets horizontally to the left and to the right. And we do this continuously. And we run many different tests with different parameters, and all of them fall into one of those 3 scenarios I will show. First one is when we have a very powerful jet. And for example, this one is 10 to the 43 ergs per second. And this jet, of course, easily gets out of the box in less than 1 million year. And you can see that it also warms up the media outside of the jet launching directions, so laterally as well, which also we see sometimes in X-ray radiation. On the other part of the spectrum, when we launch a very, very weak jet, like 10 to the 38 ergs per second, we barely see this jet going out of the very central region. Of course, turbulence sometimes creates these cavities nearby the jet injection region, so it can fill these cavities, but it cannot push further out. The most interesting part is when we have some jet that is in the middle. For example, this is 10 to the 40 ergs per second. And this jet can push through some of the walls that are nearby the jet injection region and can blow these bubbles. However, it doesn't have enough power to keep pushing them out. And also, I want to remind you that we launch jet horizontally, so along x-axis, while we see these bubbles propagating further out in almost all the directions. So let's try to explain why it happens. And here I will talk about two parameters. First one will be the location of the jet brake along x-axis. So basically the length of these arrows. So how far the jet can propagate in x direction. The second parameter will be ram pressure of the cells in the jet material and also in the medium along x-axis. And if I put all this information together and put it in one plot, here what I have. So here you can see the propagation of a jet in the white line as a function of time, and the color shows the ram pressure. And you can see that, for example, in the bottom panel, that the jet initially propagates further out from the jet injection region because its ram pressure is higher than the ram pressure of the medium. However, at some point it reaches the wall of dense material because jet, even though it's light, it has really, really high velocity. But the medium, it also has velocity, but it's slower, but it's really, really dense. And it cannot push through these walls of high density medium. So now we understand what's happening. What are the implications for the outskirts of the galaxy? And to study that, we will look at the outflows, because that's also what observers do. And so I will trace the gas going in and out of this spherical shell around the black hole. And I will plot the radial velocity distribution of the cells in this shell. And in the field bins, you can see the distribution of velocities that correspond to the turbulent box without any jet. And you can see it's symmetric because as much material goes in the box, as much as goes out. And on top of that, I have these unfilled bins that correspond to the jetted simulation. And you can see that we have outflows going outside of the box, especially in the hot phase, which is what we can expect. But also, interestingly, we also have a lot of gas going out in the warm phase, 10 to the 4 Kelvin-ish. But this is very, very high power jet, 10 to the 43 ergs per second. In the case of lower power jet, the bubbly jet, 10 to the 40 ergs per second, I'm sorry, 10 to the 40 ergs per second, we see, of course, less outflows, but most of them are still in hot phase, and I would say that it's very unlikely to measure any warm phase outflows because we have a lot of medium that just naturally has this radial velocity distribution with because of turbulence. So I think I'm almost out of time, and I want to leave you with this TLDR. So if you want to learn more about how these jets propagate in medium with different Mach numbers, or for example, with how these results are robust because of the stochasticity of the turbulence, or for example, the implications for cosmological simulations, please refer to the paper on the left. Thank you.
These jets have relativistic particles in them, and some of them propagate close to the speed of light. And you're using a hydro simulation. The question is, those relativistic particles, do they respond? I mean, what is their Larmor radius? Because if it's very big, then it's not appropriate to assume that they are a fluid, because they would, the relativistic particles would go through the surrounding gas.
So currently we don't have SR effects in our simulations, but that's something that we are working on. We are working with other repo developers to include this to our repo. But so the way we simulate jets is we just assign kinetic energy to the particles in this jet injection region, and they have velocities that are almost relativistic. So as far as we can push That would be.
Would be
I don't know.
interesting to
Yeah.
check. It would be interesting to check if the relativistic particles can deposit energy farther out.
Yeah, but yeah, we will also need to have magnetic fields then as well. So there's a lot of there's a lot to be added, definitely. Yeah.
That's the reality. It's always complicated.
Yeah, for sure. We have to start somewhere.
Comments, questions, Joe?
Yeah, so you showed that the medium power jets, they were running into walls, sometimes pressure walls. So if you had enough resolution, maybe you do, would you not see compression of clouds and induce star formation?
That's a fantastic question. So yes, we are limited with this resolution of the particles. So our simulation is Voronoi mesh, and it's adaptive mesh code. So we try to go as low mass resolution of particles as possible of the cells. And currently we are limited with the 10 to the 4-ish Kelvin gas, so we don't go further out to the molecular phase. That's why we can't really say anything directly about star formation. However, I'm now working with students in SRMP program to understand what is how jets change the turbulence of the medium, because if we have more compressive turbulence, theoretically we would maybe have more chance to have star-forming regions. But yeah, that's also interesting to add more resolution, of course. But yeah, but it's expensive, especially in jet simulation. Yeah.
Oh, okay, over there, someone was asking.
Thank you.
No?
I have a question.
So, Fabio, sorry.
I have a question about
Oh, okay, go ahead.
Olga, so this is really beautiful to see, and it seems like in that intermediate regime, something that happens is the bubbles kind of fill up the voids of the largest scale eddies. So if we look at the galaxies, are we then measuring something about like the size scale of the turbulence? If we're like looking at a bubble, and we're saying, and this is like a low density void, I don't know how we tell the quenched from the unquenched from the in the middle's observation, but if you could do that, does that help you?
Yeah, like to learn more from observations about the size of this cavities.
Yeah.
That's something that I would be really interested in talking about if if anyone wants to collaborate on that, because currently, so with the driving scale of the turbulence is 1 kiloparsec. So they're pretty big eddies, but then it cascades down as well. So currently we do have some observations of Milky Way center, so that's something I wanted to look at as well, to compare this.
See, Olga, the more you present, the more questions we could. We will not have time to address.
Okay.
Fabio, last question.
Yeah, very nice talk, Olga. I was wondering what's the longest that you're running continuously the jet, and if something like activity cycle for a black hole would change significantly what you're finding.
Yes, that's also a really great question. So the furthest we run is like 6-7 million years. The feedback really changes the environment of the black hole, so it can affect the accretion rate on the black hole and create this duty cycle. And currently I'm running the simulations with the coupled accretion rate, so we have these bursts of jets, and it's also very cool. Maybe I will show you next year. Yes.
Okay, let's thank Olga.
All right. Hi, I'm Peter Williams. So I just started a job as a technical lead at the Minor Planet Center, but for the past couple of years, I've been working on data release 7 of the DASCH project. I think it's fair to say that I'm the person who did that one data release, but DASCH itself was a huge effort, and it represents building on a legacy of actually a century of work that's happened here at Harvard. So I am standing on the shoulders of many giants. So this is a photo from literally across the hall of the plate stacks. So we hold the world's largest collection of astronomical photographic glass plates. They look like this. There's more than 500,000 of them, and they span the entire history of photographic astronomy, from the invention of dry plate gelatin to the triumph of the CCD. Most of them are about 8 by 10 inches. They are stored in shelves and paper envelopes that look like this. Harvard collected plates from observatories all over the world with a very direct intention of getting full sky coverage. The collection does cover the entire sky thousands of times over this long time baseline. One thing that I want to mention is that if you think about it, this is the world's first astronomical data center. It's an analog data center, not a digital data center. But if you look at why people were collecting these plates, the motivation for it, it's exactly what you see when people talk about modern digital data centers. And I think there's an interesting alternative history to ponder of, you could imagine a world where, like in the 80s or so, the plate stacks pivoted to become the world's first digital data center on their heritage. That obviously didn't happen, but when we talk about CFA Nexus, we're really talking about going back to something that we used to be the world leader at a century ago. So DASCH was the project to digitize all of these plates. It stands for Digital Access to a Sky Century at Harvard. It was a 20-year effort, which many of you will know was Professor Josh Grinley was the person who instigated this and led this project over these decades. A massive tour de force of blood, sweat, and tears. The image on the left shows one of the large plates, just to give you a sense of what they look like in person. The image in the middle is a photograph of the scanner, which is basically a stationary photo station. And hopefully it is pretty obvious why this is interesting as astrophysicists. Plates are weird, they're annoying to work with, there's a reason we don't use them anymore, but that 100-year time baseline is a really unique thing. And it will continue to be unique. You know, eventually we'll have a century's worth of born digital, nice CCD data, but not for another 50 years. And so what I've been working on is the final release, or not the final release, the legacy release of this project to digitize these plates. Came out just at the end of last year. The best publication right now is a archive posting, which is an ADAS proceeding submission, which those of you who are there, this talk is quite similar to that. Before I go any farther to talk about the science, I want to emphasize something, which is that these plates, so they're not just, they're scientific data items in a certain sense, but they're also cultural and historical artifacts. These plates could and should be in museums. Above all else, they're inextricably linked with the women astronomical computers. Some of the most famous names in the history of astronomy worked in this very building. I now have Annie Jumpcannon's old office. Henrietta Swan-Leavitt, Cecilia Payne-Gaposchkin. They used these plates. They were the people who built up that collection, and obviously they didn't always get the full credit that they deserved. These were some of the first women who were allowed to be scientists professionally, in a certain sense. And connecting to that, the plates are really just kind of the tip of the spear of a whole treasure trove of historical, cultural artifacts associated with this unique time and this unique, time in astronomy and also time in the history of women in science. And I think that's a really special thing about this collection. But turning back to the scientific applications, so products from DASCH include a lot of things. So the kind of core thing are these images of the plates. We call them mosaics, which is kind of confusing from sort of standard astronomical usage. It's because they're assembled out of lots of little frames. I'll start a movie of the scanner in action so you can see that. So we have just around 430,000 mosaics of plates out of that more than 500,000 total. From those, we can use astrometry.net and a lot of custom code to get astrometric solutions. They're huge on the sky. Some of them are 70 degrees tall. Distortions are rampant, so this is really tricky, but almost all of them have astrometric solutions. From there, we can match to reference catalogs and get photometric calibrations. I'm not going to go into it, but there's different ways you can do that, and essentially about 90% of those plates have those calibrations. We end up with about 24 billion photometric measurements. Depths, so they're almost all in B band. It depends on the emulsion used in the plate, which kind of sets the response. Those kinds of depths, those kinds of precision, so not very precise by modern standards, but we got a lot of them, and they do have that unique time coverage. Supporting all this is a bunch of information about like the inventory, calibrations. We have photographs of the plates themselves, the paper jackets that hold them, the handwritten logbooks that describe them, where if you think about it, those logbooks are the only way that we can know when a plate was made. Calibration, and then because this is a legacy data release, I also made a digital inventory of I can tell you exactly how many files. There's about 35 million. Exactly how many bytes. There's about 750 trillion bytes of data in all this that are documented. We have the MD5 checksum of every single file. They're all in AWS. Supporting that are things that are not part of DASCH, but again, this kind of broader network of resources. If you have tried to use DASCH data in the past, you might recognize these websites. So this is sort of the legacy DASCH way to get data. It still exists, but honestly, it is bad, and I really think that DASCH's success over the years has been held back by the inadequate data access infrastructure. I spent a lot of time trying to fix that. So now I created a Python package called DASCH Lab, which is a sort of API client plus analysis toolkit. Here's a video, so it can be used in purely standalone fashion, but it's also designed to be used in like a Jupyter Lab environment. So here, there's sort of, you can select a target area, download catalogs, download cutouts, download light curves, very AstroPy integrated. And also I put some effort into sort of integrating the code with interactive visualization using Worldwide Telescope, no surprise. And so basically because DASCH light curves do need interactive analysis, the plates are hugely heterogeneous. There's all sorts of weird stuff that can happen, especially when your astrometry, your astrometry might be good for 99% of the plate, but when a plate has a few 100,000 sources, maybe something matches weirdly. So that's like, you can't just download a light curve and trust, if there's some weird high point, this thing had a flare, like you have to look into them. So that's great. I want to show this image because I think of this work on DASCH and the plates as sort of a human chain that of care, essentially, that stretches from Josh and the current plate stack staff back to previous people here, all the way back to Annie Jump Can herself. This collection has been stewarded over the years, and we should be really proud of that. Like, this is an amazing, unique resource that we have that has been a century of people have put their lives into maintaining this, and it's not going to solve every astrophysical problem, but it is like still astrophysically relevant and contains this history of, this historical importance. Now that DASCH is done, and we can get into what exactly hasn't been digitized, but we do have 750 terabytes of data documenting this unique resource. That opens up a whole bunch of new possibilities. In particular, in an era of diversifying funding, the work that supported me was from a Smithsonian American Women's History Initiative project. And this gets into the realm of digital humanities where, frankly, they are desperate for people who are really good at technology and data analysis. But that being said, I am no longer paid to do DASCH science. No one is any longer paid to do DASCH science. So there's a huge opportunity here, but we really need, if this is interesting to you, we need people to start doing stuff, because that's what keeps that chain going forward into the future. So here are the websites. That's me. So I really want to thank, above all else, Dana, who was our former head librarian, who got the grant that supported my work, and also helped make sure that DASCH did get completed successfully, along with the rest of the library staff. And also the QR code is actually, so I've started blogging like it's 2005 again. I find it actually is a really good match to sort of trying to document stuff like working on this project. QR code is you can sign up for a newsletter. Thanks.
So Peter, can you mention one discovery or highlight that came out of looking at 100 years that we didn't know about before?
So I know like what Josh would probably tell you about is, we have imaging of 1987A, I think it's like 4 weeks before it exploded, but also, those decades before it exploded. And so, things like, okay, what happens to one of these stars before you have a supernova. What I'll also mention with my new MPC hat on is asteroid pre-coveries. So if we know where there's an asteroid right now, we can go back in the archives. And so, for instance, 2024 YR4, the thing that, if we're lucky, will kill us all in a few years. You know, right now, if you wind it back 4 years, I think its orbit is very uncertain, even to 2016. But you can imagine, you know, rewinding that orbit, and if you can say, okay, it's somewhere on this plate, here it is, suddenly you narrow down the uncertainties by orders of magnitude. So there's a whole cottage industry of people who do these pre-coveries. I think I've asked Matt Holman, I've suggested to him that he should look into it, but that particular asteroid is kind of faint, and also the uncertainties are bad enough where you would need to get very lucky. But if you said, like, okay, what are the orbits that do intersect Earth, and then wound backwards, maybe something like that would help. But yeah, if you want to, the database of all of our astrometric solutions is, I don't know, it's only like 30 gigabytes or something, and you can load it all, and basically you can do that analysis of what every single exposure has without needing to actually download every single image, which is good because that's more like 500 terabytes.
Any final comments? Yes?
I have a follow-up question to that. If I wanted to download all of the light curves of all of the objects without images, how many gigabytes, terabytes are we talking about?
The compiled light curve database is really, it's only like 25 terabytes or something. Yeah, and I've figured out ways to make that available. It might cost us some money to get it off AWS, that's sort of the trade-off, but yeah, it's a little bit of a broke format, but I've put a lot of work trying to make that sort of stuff available and usable.
Let's thank Peter again.
Just make a